Okay, 3.3, another short section. So here we go. Notice the title of this thing. Definition number 3 for our trig functions. And here they're called the circular functions, but they boil down to the same 6 trig functions. And in fact, with a definition that's very similar to the very first definition we wrote down, the one that was made up of all the different fractions of x, y, and r. All right, and when we did that one, like section 1.3, we drew a picture of an angle kind of like this, and there was theta, and we just had some point on the terminal side. We had x comma y, and then r was that distance out to the point. And we're basically looking at a same sort of situation here, except now we're only going to look at points on the terminal side that are 1 unit away from the origin. And those are points that lie in what we call the unit circle. All right? So the circle of radius 1 centered at the origin. So this ends up being your picture for our angles then. So we still can make that right triangle x and y, but it's the same situation as before, but now r equals 1. The other thing that's thrown in here is this arc length right here. So this is kind of looked at it as a way of describing sine and cosine, etc., for a particular arc length. All right, not just for an angle. Every arc goes with an angle here. All right, so r equals 1. And if we were to look at our original definitions for sine and cosine, sine was y over r, but here we have a 1 for r, so it's just the y coordinate of that point. Cosine is just the x coordinate of that point, right, when the radius is 1. All right, so we get this definition here. Theta is a central angle. So basically, if we measure this angle in radians, it's arc length divided by radius of the circle, but the radius of the circle is 1. So in fact, this arc length on the circle is exactly the same as the measurement of our angle in radians. All right, so then the definition of our 6 trig functions looks like this. You can put t or you can put theta in here because theta and t are equal to each other. So whether you're thinking arc length or angle measurement, and mostly we just think angle measurement, here's your definitions. And these are the exact same definitions we had a long time ago. It's just what you get if you put a 1 in for all the r's. All right? And that especially makes sine and cosine simple. It's just x coordinate comma y coordinate for cosine and sine. And that's why a long time ago I brought up too, think y coordinate, vertical measurements for sine, horizontal for cosine. All right, now some kind of messy mathematical concepts here. Some fancy words, which you will especially hear of when you go to pre-calculus, if you go to pre-calculus. These are functions, all right? So, and we've talked about that a lot. You input an angle, and the functions output some number, all right? Now, the domain of a function is the inputs that are legitimate for the function, the inputs that don't make something bad happen. The range is the collection of all the outputs. So for example, tangent and secant, if you look up at those definitions, tangent and secant, what they have in common is an x in the denominator. So if you put in an angle that goes with a point whose x coordinate is 0, you're going to end up dividing by 0 and everything breaks down. So these sorts of angles that give you a 0 for the x coordinate, those are angles that are not in the domain of those functions. All right, and if you measure those in radians, so where do you get a 0 for your x coordinate? Well, on the unit circle, we're talking about right here and right, let's just get rid of all that, and you. Those 2 spots. Nope, that's totally wrong. That's where the y coordinate is, 0. Where's the x coordinate 0? Right here and right here. And in terms of our radian measures, you get used to these after a while. Well, 90 degrees here, that's pi over 2. swooping around to 270, that's 3 pi over 2. Now, if you keep going, you add another 180 degrees, which is like adding pi. The angle where you go like this, that would be 5 pi over 2. And then you keep adding pi, and you keep getting fractions of pi, and in particular, you get this list that we have right here. And negatives, too, if you go backwards. So all of these angles, which are measured in radians, are angles you can't plug into tangent and secant because it makes you divide by 0. Tangent and secant are undefined there. And another more succinct way of describing that whole list is like this, noting that all of these fractions, which keeps going to 5 pi over 2 and 7 pi over 2, it's all odd numbers times divided by 2, so they all look like this. All right, likewise, cotangent and cosecant, well, they have a y in the denominator, so you can't get a 0 for the y coordinate. That corresponds to 0 and 180 degrees, and anything coterminal with those guys, like 360 and then 540, etc. So in terms of radians, 0 radians, 180 degrees is pi radians, 2 pi radians, and 3 pi radians, and so on and so forth. And when you include the negatives, you get a list like that. Or in other words, any integer multiple of pi. Now, sine and cosine are defined everywhere, so we would say their domain is all real numbers. There's nothing, you can do the sine or cosine of any angle on your calculator, and you never get a domain error. In fact, the reason some calculators say domain error is because you put in an angle that's not in the domain of those functions of tangent or cosecant or whatever. All right, the range, those are the kind of numbers that come out, and we've talked about this a little bit with sine and cosine in particular. The fact that when you do the sine or cosine of any angle, it always comes out between -1 and 1. And we mentioned for tangent, too, that actually for tangent, any number could come out. In fact, every number does come out of tangent for some angle. Same goes for cotangent, though, too. And then secant and cosecant are a little weird. They're just the reciprocals of sine and cosine. So with sine and cosine, you have a number between 1 and -1. So if you take its reciprocal, you get a number, well, these numbers in size are less than 1, so their reciprocals in size are bigger than 1. And when you have to deal with the negatives, it means you get this. Secant and cosecant, they're all either less than or equal to -1, or bigger than or equal to +1. So there's no angle whose secant is 3/4, because that's smaller than 1. Just like there's no angle whose sine is 3.5, because that's beyond 1. There's no angle whose secant is 2/3, or 4/5, or 1/9, or whatever, anything smaller than 1. All right, the last thing that we're just going to look at in this section is the unit circle. And here's where we fuse together the radian measures from 3.2, the idea of reference angles in 3.1, and now our definitions for trig functions all around the circle. So the next page has the unit circle all filled in, but I'm going to bring up a better image of it in just a sec. But the key point of this is, we'll go around that unit circle, and we'll see all these different common angles marked off. But you got to remember, x-coordinate is the cosine of that angle, and y-coordinate is the sine of that angle. And let me just show you what that looks like. Oops. There it is, all filled in. All right, so the things to notice, and this is when we're in class, I usually go through this a little bit as a class, and we watch this thing kind of come together. But what we especially end up noticing are all the reference angle families. So we have quadrant 1 here. In particular, here's 30 degrees, which is pi over 6 in terms of radians. And we found before that the cosine of 30 degrees is square root of 3 over 2, and the sine is 1/2. So there's your cosine and your sine for 30 degrees. Knowing those means you can fill out the sine and cosine values for the angles that are in the same reference angle family as 30 degrees. So all the angles around the circle whose reference angle is 30, which is 150 degrees, 210, and 330 in particular. And if you look at what we got in those pairs of coordinates, for all those angles, it's the same. Square root of 3 over 2, comma 1/2 in every single case, with the only difference being some are negative and some are positive, depending on what quadrant you're in. But 30 and 150 and 210 and 330 all have the same values for sine and cosine. It's just that some of them have a negative sign and some don't. That is the only difference. And then the same thing ends up happening for the 45-degree angle family and the 60-degree angle family. And the other thing to notice about these families are how they're similar in terms of their radian measures. So 30 degrees goes with pi over 6. And if you look at all the other angles in the 30-degree family, which you could also call the pi over 6 family, they all have these denominators of 6 that don't simplify any more than that. All right? 1 pi over 6, 5 pi over 6, and 7 pi over 6, and 11 pi over 6. And the 45-degree family, well, yeah, pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. In the 60-degree family, in radians, they all have denominators of 3. So there's all kinds of similarities here in these families, these reference angle families that we get for these guys. There's lots of cute ways of... I'm not going to make you memorize the unit circle. Some of you may have had to do that in high school even. And there's interesting ways to try and remember who goes with what and that sort of thing. What I think is worth pointing out, and I think I'll do this on the filled-in version here, as you go from 0 to 90 degrees, well, cosine starts at 1, sine starts at 0. And as you go to 90 degrees, cosine, the x-coordinate, is going to decrease because you're moving that way horizontally. But the y-coordinate is going to increase, get bigger, since you're rotating higher. And you go through those same values. So 1, and then square root of 3 over 2, get smaller for square root of 2 over 2, and then 1 over 2, and then 0. All right? Oh, and that was for cosine, as the x-coordinate gets smaller. The y-coordinate, as it gets bigger, goes through those same values. And those are our standard values. 1, square root of 3 over 2, square root of 2 over 2, 1 over 2, and 0 over 2. And not square root of 2. I don't know what the deal is there. Just want to write on you. Sorry. Square root of 3 over 2, square root of 2 over 2, 1 over 2, and 0. And the thing is, those values even have a nice pattern to them that you can see if you write these a little differently. So I'm going to leave these two the same. But the square root of 1 is 1, so 1/2 you could even write as square root of 1 over 2. And 0 you could actually write as the square root of 0 over 2. And 1, well, square root of 4 is 2, so if you divide by 2 you get 1. So these 5 common values that we see actually perfectly fit this pattern of fractions with a denominator of 2 and square roots on the top, and they just go up from 0, 1, 2, 3, and 4, like so. So when you're thinking about what the right measurement is here, the way I end up looking at these guys is, well, y coordinates. 30 degrees is the small one. I know it's not 0, but out of these three angles here, 30 degrees would be the least tall, so that would be the square root of 1 over 2. 1 in the middle is square root of 2 over 2, and then square root of 3 over 2 for the higher one. Now, out of those three angles, the x-coordinate is biggest for 30 degrees. It's furthest to the right, and then they get smaller, and then they get smaller. So it would be square root of 3 over 2, and square root of 2 over 2, and 1 over 2. So that's how I think of them in my head, at least. Now, like I said, I'm not going to make you memorize these things. You'll have your calculators. You punch out something and get 0.866. You should know that's the square root of 3 over 2. And square root of 2 over 2, good old 0.707, if it comes out like that. All right, so there's the unit circle. And it's important to understand all the relationships between angles in the other quadrants to the angles in the first quadrant. And anyway, just be able to use those guys. All right, that's 3.3.